Microwave tubes, traveling wave tubes, part 2, series on microwave engineering, lecture number 4.42. Traveling wave tubes are microwave amplifiers. They are well known for their broadband nature. They are also well known for their higher gains. They employ non-resonant circuits to provide interaction between the signal and the electron beam in a continuous manner to achieve higher levels of gain. In the present session, second one on traveling wave tubes, the focus is mainly on the functioning. A detailed description of the working of TWTs and two equations, electronic equation and circuit equation, which provide analytical relations for describing the interaction that exists between the signal and the electron beam. In the present session, we also consider the operating characteristics of TWTs. They include different regions in the operating characteristic of the device and also AM conversion, PM conversion. Now we move further to the core session to study, to understand the device deeply, more clearly. Let us start with a few points on the functioning, working of the device. The signal to be amplified is given to the helix at its input end. Here it is assumed that slow wave structure is a helix. Other slow wave structures are also possible. To describe the functioning, we have to consider one or other helix structure, one or other slow wave structure. Here we considered helix. So this is helix. Signal input is given at one end, it is taken out from the other end. For the sake of simplicity of analysis, here only one component of the signal is considered as input. Signal means several components. A single component cannot be a signal. Signal by definition is a waveform which is capable of carrying information. Single component cannot hold any information. Therefore, conclusion is single component cannot be signal. But here we consider a component of the signal as input for the sake of simplicity of analysis. As this component travels through the helix tube, there comes into being a spatially periodic traveling wave coaxial to the helix. When the single component travels along the length of the helical coil, there comes into being a periodic waveform, spatially periodic waveform along the axis of the helix. Also notice, while the device is functioning, there exists a beam also, electron beam also along the axis. Now, a spatially periodic wave is coexisting with an electron beam along the axis of the device. The electron beam is initially accelerated to a velocity which is slightly more than phase velocity of this axial wave. This is an important aspect, slightly more than phase velocity. The signal, as it travels with a velocity equal to velocity of light. But as the helix is a slow wave structure, it reduces the velocity, phase velocity of the signal along axial direction to such levels where it is traveling almost with velocities with which the beam is traveling. So axial signal and beam, they are traveling almost with same velocity. Here it is said that electron beam has to be made to travel with a velocity which is slightly higher than phase velocity of the axial wave. As both the periodic spatial wave and electron beam are coaxial and traveling almost at the same velocity, mutual interaction takes place between them. For interaction to be there, both participants must be traveling at the same velocity or almost same velocity. Here they are traveling at the same velocity, so interaction is possible. As a result of interaction, energy exchange between wave and beam occurs. Notice here, energy exchange means both directions. It includes both the direction. Energy can be transferred from beam to signal, and it can be in the opposite direction also, from signal to beam also. But the amounts become unequal, and there comes into being more or net energy transfer from beam to signal when certain conditions are satisfied. We are going to see those aspects. From the polarity of axial wave, the wave accelerates the electrons during one half cycle, giving energy to beam, and decelerates them during next half cycle, taking energy from the electrons of the beam. The electrons, due to acceleration, they are able to cross the accelerating half cycle quickly, whereas they take more time to cross the decelerating half cycle. Here is shown the energy transfer mechanism between beam and signal. We consider one cycle of axial signal, positive half cycle, negative half cycle. Let us say during positive half cycle, the electron beam is decelerated. During negative half cycle, electron beam is accelerated. Let us concentrate on retarding half cycle, that is positive half cycle. As electrons are getting retarded, their velocity gets reduced. They start traveling slowly. It leads to accumulation of electrons in this half cycle. When we consider accelerating half cycle, here electrons get some acceleration, though, so they start moving somewhat fast. So they cross this half cycle quickly. It leads to reduction in electron concentration in the accelerating half cycle. To have more understanding, deeper understanding, imagine the situation of this entire frame moving from input end to output end. Entire structure keep on moving. While moving, electron concentration in the retarding half cycle keep on increasing. Electron concentration in the accelerating half cycle keep on decreasing. Ultimately, by the time this particular frame of one cycle reaches the output end, there exists high electron concentration in the retarding half cycle, implying the formation of electron bunch. Hence, bunch formation starts at the beginning, and it keep on growing as it travels towards the output end. While traveling towards the output end, it keep on interacting with the axial field. It keep on getting retarded by one half cycle of the axial field and keep on delivering energy to the axial signal. If we consider the electrons that exist in the accelerating half cycle, as already mentioned, as electrons get acceleration from the field, they move with higher velocities, they cross this half cycle quickly and then enter into the retarding half cycle. Net result is very few electrons in the accelerating half cycle. Electron concentration in this half cycle keep on decreasing. It may become almost nil by the time this frame reaches the other end. Net result is, as electron density, as electron concentration decreases, the energy that is taken from the axial field by the electrons for getting accelerated also comes down as the frame moves towards the output end. So in one half cycle, energy transfer happens from beam to signal, and this transfer keep on increasing as beam travels from input end to output end. In the other half cycle, energy transfer from signal to electron beam keep on decreasing as the frame travels from input side to output side. So at any point of time in the steady state, we can notice that there exists transfer of energy from beam to signal, net energy transfer from beam to the signal. So signal gets strengthened. So the charge density and signal rise both are sketched here in B. Some more points regarding the functioning. It results that at any point of time there exists more electrons in the decelerating half cycle, resulting in a net transfer of energy from electrons to the wave. The strengthened wave further offers much more deceleration to the incoming electrons, increasing electron concentration in its region, thereby increasing energy transfer to the beam manifold. It results in the exponential growth of signal along the length of the helix. Brillouin diagram. What is this Brillouin diagram? It is omega beta diagram. Omega is angular frequency. Beta is phase shift per unit length. In any wave, there exists time variations. There exist spatial variations too. Time variations are described with the help of omega, angular frequency, whereas spatial variations are described by beta. Omega is 2 pi f. F is linear frequency, whereas beta is 2 pi by lambda. Lambda is wavelength. And F and lambda, these two are related, we know very well. In any wave phenomena, F into lambda is velocity of the wave. With this understanding regarding omega beta, now let us go to see what is Brillouin diagram. What is its use? What is its relevance as far as PWTs are concerned? The Brillouin diagram is omega beta diagram. It represents the relation between angular frequency and phase shift constant beta for a helical slow wave structure with several spatial harmonics. The second quadrant of the omega beta diagram indicates the negative phase velocity that corresponds to negative value of n, the mode number. The shaded areas represent the forbidden regions for propagation. The wave is prohibited in these areas because here the phase velocity exceeds the light velocity. Note that if the axial phase velocity of any spatial harmonic exceeds the velocity of light, the structure starts radiating energy. In this slide, he is talking with reference to a diagram. This is the diagram about which a few points are given in the previous slide. Horizontal axis represents beta, vertical axis omega. There are some triangular areas. Here is a label forbidden region with respect to this diagram. He is giving some points. Let us once again go through those points. The second quadrant of omega beta diagram indicates a negative phase velocity that corresponds to negative value of n, the mode number. Second quadrant means this -1, -2, -3. These are mode numbers. The shaded areas represent forbidden regions for propagation. This is a shaded region. It represents forbidden region. Why it is forbidden? These regions represent phase velocities exceeding light velocity. That's why these are forbidden. After Brillouin diagram, now let us move to another aspect. This is about interaction. Interaction is the cause of energy transfer from beam, electron beam, to the signal. Here, the interaction refers to the interaction that exists between electron beam and the slow wave structure. Here, the slow wave structure is helix. Here is shown electron beam. This is electron beam. Here is shown by its side a helix denoted by its equivalent circuit. Helix is a transmission line, a lossless transmission line. Equivalent circuit of lossless transmission line consists of several sections, each section consisting of an inductor and capacitor. Electron beam is a beam formed out of negatively charged particles. These particles are moving at high velocities. Therefore, beam is actually a current. It is current. That current here it is denoted by small I. As it is, when the beam is unmodulated by the signal, beam represents DC. No variations exist in the current. That current is capital I. Due to interaction, the signal generates an AC component in the beam current. Then the beam is DC plus AC. So an AC with a DC component is traveling through a transmission line. Certain voltages come into being, certain currents also come into being over to the line in addition to the input signal, current and voltages. Therefore, a component comes into being into the helix structure due to the beam current. One can easily notice now from this discussion, from this argument, that presence of signal in the helix, it affects the beam current. Beam current in turn affects the signal that is traveling over the helix. So the interaction is mutual. There are two equations, two relations, namely circuit equation, electronic equation, which describes completely the mutual interaction that exists between these two, that is beam and slow wave structure. A few points regarding electronic equation. What is electronic equation? It is an expression for the convection current I induced by the axial electric field E1. I is equal to J beta E I naught to V naught J beta E gamma whole square E1. Simply, it is an expression for the current that is induced in the electron beam by the axial signal field, where gamma is propagation constant. It is equal to alpha E plus J beta E. Alpha E is attenuation constant, beta E is phase shift constant. Beta E is phase shift constant given by gamma naught equal to gamma with I equal to 0 and V naught I naught are DC beam voltage and currents respectively. Circuit equation. The circuit equation gives connecting relation between axial electric field Ez and AC electron beam current I. Ez is something multiplied by I. What is this something? Z naught, gamma square minus gamma naught square. Here Z naught is characteristic impedance of the helix. Axial signal impacts beam current. Beam current in turn impacts axial signal. The impact is mutual. The impact is described by electronic equation and circuit equation. How axial field gets affected by current, that is given by circuit equation. Now a few points regarding operating characteristics. Here are shown two diagrams A and B. In A, a sketch is given which describes RF input versus RF output. This is transfer characteristic. One can see here linear region, saturation region, dynamic range, etc. In B is shown RF input over one axis, AM on one vertical axis, and phase length on another vertical axis. Some points now we consider to understand a little bit deep regarding the functioning of the device under operating characteristics. The operating characteristic of TWTs is marked by two distinct regions: linear region and saturation region. Linear region, also called small signal region, is most often defined as ending when increasing RF signal causes gain to drop 1 dB from its small signal level. 1 dB compression point. Saturation region generally occur at an input drive level 6 to 8 dB above 1 dB compression point and with 2 to 3 dB higher output power. Linear region, saturation. The dynamic range is the region between the points at which the RF output signal just breaks through the noise threshold to the point at which the output power saturates. Linear region is the region where the device is supposed to be operated. Some more points regarding operating characteristics. The AM conversion and PM AM conversion are two important phenomena which are essential in understanding the functioning of traveling wave tubes. AM conversion is a measure of the change in RF output power due to a change in the RF input drive, and it is given by the slope of the transfer curve. In the linear region, this conversion is 1 dB per dB, and at saturation it is 0 dB per dB. TWTs with a high interaction efficiency often exhibit gain expansion near the high band edge, that is AM to AM more than 1, due to the mismatch between helix velocity taper and beam slowdown at all the in-band frequencies. It is hardly desirable to operate the tube deep into overdrive as it causes severe beam defocusing in this region. So overdrive should be avoided while operating the device. Now, a few points regarding AM-PM conversion. The AM-PM conversion is relatively insensitive to input signal level in the linear region. However, when TWT is driven towards saturation, the rate of phase change naturally increases. The peak value of AM-PM generally occurs at or several dB below saturation, and it is frequency dependent too. If the factor that changes beam velocity varies with time, the result is phase modulation of the RF output signal. The primary factor affecting the velocity of beam is cathode voltage, whereas other voltages or external factors have secondary effects. These are some of the important aspects pertaining to the operation of traveling wave tubes. This is what I have. This is what I want to share with you for right now. To recap, in the present session, we focused on the functioning of the device, how it is able to provide amplification to the signal given at its input terminals. During the functioning, there exists mutual interaction between electron beam and the input signal. This interaction is described by two equations, electronic equation and circuit equation. These two equations are introduced. Some important significant points regarding the operating characteristics of the TWTs are also described in the present session. Enough for now. Hope you have enjoyed the session. See you again soon in another session. Bye bye.